Hello everyone. In the last video, I've shown you how addition is done in binary using the binary table that we have prepared previously. We also have shown how addition is done differently in fixed point and floating point numbers. In this video, I'm going to introduce you to subtraction using binary numbers. First, I'd like to emphasize that there's no direct subtraction that is used in binary. That is because there's no hardware that supports it. Instead, subtraction in binary uses addition, the same addition process. However, before the addition is done, the subtrahend is converted into a negative number. So in this video, I'm going to show you how negative numbers are represented in binary. Okay. How is binary subtraction done? Of course, we can do that manually. It's just like a binary addition. So for example, we can apply the law 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. But 0 minus 1 equals 1. Okay, it's like a bar of 1, like 2 minus 1. So it becomes, the bar of 1 is like a 2. You deduct a 1. So it becomes 1. Okay. For example, we have the following values. 123.75 minus 85.5. We are not yet converting 85.5 to a negative number. So 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 0 is 1. Now 0 minus 1 cannot be. So we will borrow the 1 in the left. So this 1 is actually a 2. So when we say 2 minus 1, this is a 1. And this borrowed 1 becomes a 0. So that 0 minus 0 is 0. 1 minus 1 is 0. And 1 minus 0 is 1. And 1 minus 1 is 0. So if you convert this is 38.25 because 0, 1 is a 1/4. And we have a 1, this 2 plus 4, which will give you 6. 6, 8, 16, this 1, 2, 4, 8, 16, 32. So 32 plus 6 is 38 plus the 0.25, you will have 38.25. Okay, that's easy to do actually manually, but in hardware, subtraction is not supported because you cannot support two different configurations at a time. It will complicate the hardware. Before we introduce how negative numbers are represented in binary, we'd like to show an important property or several important properties of binary numbers given a certain range. Okay. The maximum value, if you have an n-bit binary number, okay, a binary number with n bits, the following properties apply. Given n bits, the maximum value is 2 to the n, 2 raised to the n, and later deducted by 1. For example, when n is equal to 4, we know that the highest value at 4 bits is 1111. Okay? And this is 2 to the 4, being 16. Minus 1 is 15. Actually, the last place value here is 1248. There is an easy way to remember that. You get the next place value. For example, if the most significant bit, in this case, has a place value of 16, or rather 8, 1111. So the most significant bit has a value of 8. The next value is 16, right? The next value is 16. We just subtract it by 1, so it's 15. Okay, we don't even have to raise it to an exponent of 4. We just determine the next place value. Okay. So for example, the place value of the most significant digit is 2 to the n minus 1. In this case, n is 4, so we have 4 minus 1 is 3. Okay, 2 to the 8, which is 8. 2 to the 3 is 8. For example, in the value 1111, okay, the most significant place value is 2 to the 4 minus 1, or 3, which is 8. The most significant bit has a place value of 8. Now, it is important because we use these properties to compute for the ones complement. What is the ones complement? Given a range, a fixed range of bits, okay, there will be pairing of binary numbers automatically. It's a wonderful property that binary numbers pair them together. They're called the ones complement pair. Okay, let us try to find what this is. So, for example, given two n-bit binary integers, if they have the same bits, okay, if two numbers are of the same bits, okay, they can be said that two numbers can be pairs or one cons complement if their sum is 2 to the n minus 1. Okay, if they sum together as 2 to the n minus 1, 2 raised to the n minus 1, then they are pairs. They are called ones complements. Okay, for example, we are given the value 101, 1010. What is the ones complement? We know that the 2 to the n minus 1 here is 15 because n is 4. We have shown that already, right? 2 to the n minus 1. And what is the value of this? 1010. 0, 1, 2, 4, 8. This is a decimal 10 because we have a 2 and an 8. Okay? So, therefore, the ones complement pair of a number is the maximum value minus its value. For example, the value of x here is 10 and the maximum value is 15. Okay? So, we will subtract 15 minus 10. Okay? 15 minus 10 is 5. We get 15 as the maximum value. So in this case, 10 and 5 are ones complements. They are pairs. Okay? 10 and 5 are ones complements because 10 plus 5 is 15. Okay? We also know, for example, that 9 and 6 are also ones complement. 9 and 6 because they equal to 15. Okay? You can also compute 8 and 7 are ones complement pair because they are summed together as 15. Okay? I hope it's clear. So take note that the binary value of the value 15 is 1010 and the binary value of 5 is 0101. I know you notice a characteristic here, but we will emphasize that together. So in this case, we know that even if you use the value 6 and 9 or 8 and 7, when you convert them into binary, you will notice a repeating property, which is that the ones complement of the number is computed by flipping zeros to ones and ones to zeros. For example, if we flip the bits of 10, 1010 into 0101, that equals 5. Okay? So you don't have to determine even the maximum value. That's a very important property of binary numbers. For example, we have this. What is the ones complement of 123? Okay, 123. Okay, how do we know that? Uh, the highest place value, okay, at at uh, at this number is 127. Okay, that is let me find that out. 1, 2, 4, 8. So this is already a 15. Okay, 15, 16, and 32. Okay. So anyway, the ones complement of 123 is the highest value 127 minus 123. So the highest value, I'm not sure if it's 127, it's all ones here. Okay, if you subtract the highest value, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0. So take note that, okay, 123 is 111,001. If you sum that together, they will be equal to the maximum value. And they're also a flipping of zeros and ones because the highest place value is 128. Okay, so the highest place value is 128 minus 1, it's 127. That's why we are subtracting 127, which is the highest value, minus this, and we get the pair. Take note, the maximum value minus the number gives its ones complement. And we can also compute it by just flipping zeros to ones and ones to zeros. Okay. Now that applies to only to whole numbers. How about the binary fractions? For example, given an n-bit binary fraction, 3 bits, 0.1111. Okay. Well, how do we compute the ones complement of the binary fraction? Okay. So, for example, what is the ones complement of 0.01, points 0.101? Okay. So, for the first one, we'll have a 0.5. For the 0, we'll have a 0.25. Okay. And for the 1, we will have a 0.125. Okay. The highest value here, if you have 0.111, the highest value is 0.875. Okay. So, if you are going to subtract 0.875 with 0.625, okay, take note, we are computing the using the highest value. The highest value is 111, okay, and 101 is 0.625. So the highest value of 0.875 minus the given value of 0.625 equals 0.25. If we convert, okay, if we convert 0.25 to binary, it's 010. Take note that incidentally, what applies to the integers will also apply to fractions. That the ones complement of fractions can also be computed by flipping zeros to ones and ones to zeros. Okay, that's a very important property in order for us to understand the process of subtraction. Okay, what is a two's complement? Okay, the two's complement is actually our format for representing the negative value of a positive integer or even a fraction. Okay, the two's complement of a binary number is its ones complement plus 1. Remember that you first compute the ones complement and you add 1. For example, what is the ones complement of 2's complement rather of 1011? Okay, the ones complement of 101, the two's complement is its ones complement. So if we do a flipping of zeros and ones, so the ones complement is 0100, we add 1. Okay, so the two's complement is 0101. Okay, now the wonderful property of two's complement is that if you reverse, if you do the same process to the result, it will bring you back to its original form. For example, we have 0101. Okay, we find its ones complement, which is 1010. We add 1 to it, we have 1011, which brings us to the original value. Okay, so repeating the two's complement will just repeat the cycle. It will give you the same result. It will flip from one result to another. So remember that the two's complement is the negative representation of a binary number, because in order to subtract, okay, we will convert the subtrahend into two's complement and perform addition. Okay, only addition is supported by hardware. Even ALUs and FPUs can only do addition. However, they can perform subtraction by converting the subtrahend into its two's complement form. Now we have the following table. You can look this up from our regular class. It's important, it's very important that you can memorize them. Okay, given a decimal value representing an n-bit binary number, you can have a formula to compute. This is a special problem. Can you find the formula to compute the ones complement and two's complement? Yes, because we know that ones complement is just the maximum number minus itself. Okay, and the two's complement is adding 1 to the ones complement. So therefore, you can easily make an Excel formula that will automatically convert, okay, a whole number, binary number, into its negative form, which is two's complement. Now, how do we compute the two's complement of a binary fraction? Okay, we do the same thing. We flip, okay, ones to zeros and zeros to ones until the least significant bit. Okay, and we add 1 to the least significant bit. Despite the fact, even if it's 0, no, we always add it to the least significant bit. Remember that, to the last bit, to the right. For example, if we are asked to find the 2's complement of the value 123.75, okay? We know that 123 is 1111011. We know that, no? And 0.75 is 0.11. It's because it's 1/2 plus 1/4. Okay. So to find the ones complement, we flip the ones to zeros and zeros to ones, and we add 1 to the least significant bit. Remember that the bits here, the least significant bits, are both zeros. Where do you add the 1? To the last zero before your to the last one before you complement, you computed the ones complement. So therefore, the 2's complement in this case, no, is 0.01. Remember, no, the least significant bit of the original number. Okay, so now we can compute, no, the 1's and 2's complement of both integers and fractions in binary. Now, how do you convert back? How do you convert back? For example, is there an easy way? No, it's yes. Okay, you don't have to add 1 and repeat the same process. Okay, given if you know that a 2's complement, rather binary number is in 2's complement, how do you convert it to decimal? Okay, now here's the rule. If the most significant bit is a 1, compute the binary sum of all the MSB with compute all the binary sum of all bits, no, of all bits with the MSB assigned a negative value. I hope you follow. No? So take note of this. Look at the MSB. Okay? If it's a 1, you assign it a negative value and compute the sum. If it is a 0, okay, you extend the most significant bit to the next higher bit, okay, and assign it a value of 1 and a negative place value. Okay? Let's have an example. In this case, we have a value of 11011. The place value of the first is 1, the second value is 2, the second value is 4. Anyway, it's a 0. The next place value is 8, and the next place value is 16, but we assign it a negative value. Okay? We assign it a negative value because we know that this is given to be a number in 2's complement form. Okay? It has to be assumed, no? It has to be given that this number is in 2's complement form. Since we know that this is in 2's complement form, we assign the most significant bit of the a value of a negative value. So you have negative 16 plus 8 plus 2 plus 1, which will give you negative 5. Okay. On the other hand, if you have the value 0, 1, 1, 1, 1, so the most significant bit is 0. That's important in a 2's complement form. No? The most significant bit, even if it's 0, is important if it's in 2, even if it's in it's 0, because it's in 2's complement form. We will extend a 1 to the most significant bit. This time, assign it a negative value. So this is a negative 32 followed by a 0, which has the place value of 16 plus 8 plus 4 plus 2 plus 1. So in this case, the actual equivalent of the 2's complement form is negative 17. Now, can we apply this method with binary fractions? Okay. We'll find that out in the next video. Actually, we can do that also, no? By actually converting into 2's complement form. Thanks for watching, and in the next video, we will convert into 2's complement form and do subtraction. See you then.